Right, welcome back everybody. This is Physics Intro to Graphical Interpretation. So for this week, we're going to be looking into graphics. You've learned how to graph. Let me try something, full-scale production over here. You've learned to graph mathematics, graphics in your math classes. And the reason, right, for that is that you can then extrapolate information, which means you're going to look at a graph and it's going to tell you a whole story. We've been doing this a lot in all of science. This graph here, after a lot of experience, and you will get that too, this graph here tells me something, tells me many things. And we can talk about a few things. So the goal this week in physics, especially, will be to graph some data, plot graph, and extrapolate information. I want to introduce you to this note so that you better understand it. So I've taken this data here. So let's say that an object is going to be traveling 14.4 meters. And this is the time that it will take in seconds. You'll notice that there's a direct correlation between the problem. Great. You'll notice that there is a direct correlation between those numbers and those numbers. And that's okay, because this is the homework. And I want to give you an example that looks like the homework. You get a better idea of what things mean, etc. Plus, it's not super easy, so we're kind of doing the first problem together. So, say we're doing an experiment, and an object is rolling, and there's a person at 0 meter, 2.4 meter, 4.8 meter, and they're taking a note of the time, and they see that at 2 seconds, the first person takes a note. At 4 seconds, the second person takes a note. Or at 4.8 meters, the person takes a note at the time. And we could end up with with data like this. So if a person, so what probably happens instead is everyone here has a watch, and at 2 seconds they would be able to laser point the exact position of that rolling ball, and then they can say, well, that's 2.4 meters away from the start. And then another person, or the same person, if they have 1,000 hands and 1,000 eyes, they can take another measurement and say that was exactly over there, and they can measure that at 4.8 meters. Do I need to draw this? So the object rolls. The first person says go. The object has not traveled. The time is 0. And then after 2 seconds, the object is here at 2.4 meter. After 4 seconds, the object is here at 4.8 meters. After 6 seconds, the object is here, 7.2 meters, and so on. And that's normally all that we can do when we do an experiment, right? We only have 2 hands. We can only do 2 things, or 1 or 2 or 3 max, right? We can't plot a graph as this is happening. So all I can do is, I can see it. Oh, I see it over there, and then I stop my graph, my note. Oh, I see it over there, and that's really all we can do. We're just humans. If you have computers with a bunch of cameras and lasers, you can set, and you have a few engineers around. You can say, "Let's go," press a button, and then they take measurements, right? But it is what we can do, and you could, if you want, organize a setup where you're the only person who takes a note, and you have to restart your setup and then take your note, and then after 4 seconds you take another note, and you end up with a board like this. Okay, what do you do with that? Well, you have to put them on an axis, both on two axes. So you have the time here, which will be our x-axis. Time is often, in physics, more often than not, your x-axis, because you can easily follow that, right? The time flows like this on that graphic over there, and what happens on the x-axis, on the y-axis, is what matters. So as time flows, y keeps going up, right? So as time flows, y goes up. Can I do better? So as you can see here, as time goes by, 1, 2, 3, 4, 5 seconds, 6, 7, 8, 9, 10, what happens to y? Well, it depends where the points are. As you increase in time, your y also increase. This point, and I think at this point, oof, okay. At this point, time, we have a certain y value. This point, time, we have another y value. What are those values? Well, right, so this is what the graph is telling me. This is telling me, well, this is at 1, 2, so 2 seconds. We have a value of, and if we'd be really good with our eyes, we could see with eagle eyes. For now, we have to resort to the data that is right here. 2 seconds, 2.4 meters. 2.4. At 4 seconds, 4 seconds, we have just under 5. 4 seconds, it's 4.8. So you can see how to graph this. Say these points were not here, you would simply take the third point, fourth point. So at 6 seconds, have 7.2 meters. First axis on the x will be the time. Maybe we should draw that. Let's just make a little draw here. From the start, I'm limited with my functionalities. Okay, so because we have two axes, we're going to make straight lines using the rulers. Not sure how to do this here. And then we're going to graph. Using a ruler would be better here. 5. Not even 5. 5 is not even a good. You could do 6. Or because it's going to end, we have to look at where it's going to end. This is the end. So because it ends at 12 and we have 4 lines, might as well put 12 here. Because 12 divides by 4. 9, 6, 3, 0. So it's your choice how you divide it. It's a matter of how long you have, and maybe counting all the spaces. Paper. I know there's tools for that. I'm not sure where they are. He finds them. And try again. I'd like to try again. I don't know how to make a straight line with it. Kind of good. That'll be good for now. Arrows, zeros. Okay, so now we can actually count them. So 1, 2, 3 would be so how many do we have? We have 1, 2, 3, 4, 5, 6. 6 here, about 12 here. So we have enough on the x-axis to put 1 square per second. That's because my paper allows me, and my surface allows me. So we could do what I was encouraged to do when I was a kid, was to do them all. It's kind of long. Radius. 1 second. We're not going to write second every time. We're going to write time here in seconds. 1, 2, 3, 4, 5, 6. You get the idea. What we need is 2, 4, 8, 6, 8, 10, 12. I'm going to skip here. 8. Skip that and write 10. Skip that and write 12. Now that's not super pretty. The goal here was to save time. The goal here was to be super precise. Not the same goal. What you should be doing is choosing. You want to put all the numbers or just those that matter. Like these. I only put what matters. But you get the idea. What about the distance? The distance goes to 14.4. So if this is 14 and this is 15, and my point is going to go in between the two, then I need more than 14 because it's 14.4. So I want to end with 15 or 6. I can already see that I don't have enough square. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's not enough. We should extend this line further. These are the kinds of details that worry about. That should do. So I have at least 14 squares. If you don't have 14 squares, then you want to 2 per square. Should have 14 squares. So 1, 2. What do I do? I'll do ones because I'm going in between, like I have 2.4, 4.8. I'm going in between numbers. I'm going to organize them all. It's got to be 15. And this axis is what? Instead of writing 0 meter, 2.4 meter, this is the distance. In meter. things here. I'm gonna do tree graphs just to give you a flow for things, but I want you to write one graph. That's all you have to do. You can do two, but it's 7, 8, 9. You can see the problem that I'm having. I'm writing too big. Because of that, could either focus. We have that technology. But I do think the notes is going to be pretty small. I don't know. I guess you'll be all right because you're using the same program. 14. Look at that. What would we do now? We've done a nice base graph. We have our axes, we have scale, we have our units, and the arrows, and a description of the app. Now we're going to take that data here, the same data, put it here. It's very simple. You just follow an XY. So basically, this is a point. A little difficult. This is a point. This is another point. Right, that's another point. That's a visual idea that I hope you'll never forget. Your table are points. 0, 0, 2, and 2.4. What you do is you come here. So 0, 0. Here. Can we make this bigger? Nice. The next one was 2 and 2.4. You can see here. 2 on the time axis, that's X, that's why X and Y, and it's well organized, and we have time first, and Y for X first, and Y first, second. Okay, 2 and 2.4. Go on your graph. 2 here. Kind of follow that line until you reach 2.4 this side. So 2.4 is before 2.5. It's a little bit before that. Could be here, kind of, sorry, and follow that idea. Here and here, hit this. That's next point, please. 4 and 4.8. 4 is here. Oh, kind of moved a bit. Move it back a tiny bit. 4 along those lines. Then 4.8 is just before 5. 4.8 is 4 and 4/5. Grew up right off a fifth here. That line just before 5. Dot. The more precise you are with your dots, recognizing the scale, respecting the scale, the nicer the graph will. Move this here. Oh no, I'll keep it. Okay, so we could continue this. It's just long and boring, and it's already here. Now what? Well, this is the result that you should have from something like this or the past one. Sorry. Okay. So basically, this is the result of our data. This is something you've done in math. There's nothing new about this. You don't need seconds here. What's new? What's new? What is new is going to be the insights that we get from this. So first we're going to draw a line to link our points. They all fall on the line. That's really interesting. Not only does it say that the object was going at constant speed because the line doesn't change, but it also means that whoever did the experiment did a very good job at taking data. Normally we would expect the dots to not fall exactly on the lines because there's a little mistakes on and imperfection, human nature. Okay, so we draw this. And what can we do with that? Just take this, bring it here. Yeah, okay. So what can we do with this? Just this here. Well, we can start answering questions. Like, for example, I can ask, what happened at 10 seconds? No. Is this better? What happened at 10 seconds? You look on the graph. Let me move my face here. Let me move the graph. Yeah. So if we look at 10 seconds and follow the line, say, well, the object was at 10, 11, 12. The object was at 12 meters. Exactly 12 meters, because it's on the line. What happened at 5 seconds? Well, the object was, and you come from 5 here, you go up here, and you can say, well, the object was at 6 meters. What happened at 15 seconds? Ah, that's interesting. So the experiment stopped at about 12 seconds. See this here, or should I say there? You can see that the object or the experiment stopped at 12 seconds. But we can ask ourselves what would have happened at 15 seconds. What would have happened in an hour? Right? These are questions that we may ask. So at 15 here, we would simply go at 15 seconds, follow the line, from here, follow the line up. And if this line would continue, if we could draw a nice line, we would probably get something like this. And we could say at 15 seconds, the object would have been at 16, 17, 18 meters. So we're just looking at a graph and answering questions using a graph. Have you noticed? We're just using the graph to answer questions. Right, so when it says here, draw a graph, that's what we did. And they tell you which axis is what, and then use the graph, find the travel after 5, using the graph, find the time. There's no math here. It's just, what does the data tell you? And then we can ask, was the speed constant? So if the object kept moving, and it's at the distance that he traveled, this is important. If you get everything from now, you're good. We're gonna close in a little bit. So how do we determine if this straight line represents a constant speed. So what's interesting for us is, did the object travel as far every second or not? There's two ways to do this. We could we could do this here. Simply say, what was the change from this point to this point? It was plus 2.4 meters. And we have to ensure that we can also ask ourselves how much time was spent. Plus 2 seconds. I put a plus because the object could be going backwards, and that matters. Right? If the object goes to 12 and then goes back to 0, that's going to change our graph. Okay, so nice. That doesn't tell me anything. You're right. Let's continue. From this point, this is important what we're doing right here. From this point to this point, how much did it increase in distance? So we just do this minus that. 4.8 minus 2.4 is plus 4.8. Sorry, 2.4. I'm kind of busy. I want to remove this grid behind you because I don't think you can see. Okay, better. And the next one, from here to here, did it also increase 2.4? If you just add it up, this plus 0.4 is 5.2, and this plus 2, 7. Yes, 2.4. Well, that means that the data tells us that this side is increasing evenly, but we have to make sure that the other side is also increasing evenly. You guys are good? Okay. Because if this side increased 2.4 meter, but then this side increased by 3 seconds, and then here it would take another 10 seconds, then there's no way it would be at constant speed. Right? But we are in a lucky scenario, or a nicely drawn out scenario, where everything takes 2 seconds. So it's even here, and it's even here too. What does that mean? That means that it's increasing its distance consistently over time. No change. What does that mean if something increases distance over time, no change? They're going at a constant speed. This is not a study about physics right now. We're really studying graphs. How does that draw out? How does that draw out on a graph when you go at constant change? Constant change. Well, you would be looking at a straight line, right? Let's draw it out. This is our plus 2 seconds. Plus 2 seconds. Plus 2 seconds. From our graph, from our data. Yes, I'm trying. Right, so as you can see, this is an increase of this side by constant increase. And on the other side is also constant. See? Okay. From here to here, we have 2.4 meters. from here to almost here, another 2.4 meters, and from here to here, another 2.4 meters. So as you can see, if I want to increase by 2.4 meter and by 2 seconds, and then I want to do that again on each point, 2.4 meters, 2 seconds, meters, then there is absolutely no geometrical way to not draw a line. So this is called a linear motion. Linear equations are also going to pop out of these types of movements. They are the most popular graphs in mathematics. They are linear equations, linear graphs. Yeah. There's a few special things that they noted about this graph that we can do, and it's called the slope. This is the last thing I want to show you. So the slope is going to be a way to tell by how much it's going up. Is it going a little bit up, or a lot up, or is it going down, or a lot down? That's the slope, and that's a number. And interestingly, the slope of this graph happens to be, well, interestingly enough, the slope of this graph happens to be the speed that the person is going. So that's very interesting how we can take data, make a graph, and then take a formula that's made for graphing, mathematics, and it gives us a physical answer. Physical answer. That's really intriguing. So let's take a look. The slope formula is the most important one for a linear graph. So a slope has multiple ways to be written in math. We will call this in Math 9 or Science 9 rise over run. It could also be, well, we'll see what that means. So the rise over the run. So by how much did I rise for that amount of run? So for example here, we rose from the first point to the second point. We rose how much in the y-axis? It's the rise. We rose plus 2.4 meters. Yes. Not perfect. Not perfect. Continue like this for now. We rose 2.4 meters. And we ran how much for that rise? Plus second. Notice here the plus plus cancel out because it doesn't matter if they're there. There's no minus. 2.4 divided by 2 is 1.2. Oh, what happens to the units? Well, they stay like this. Write them here. Per second. And that's probably the thing that stroke the scientists at the time, Galileo and Copernic and all these folks that used graphs and data to see that the slope is actually useful. So they started doing the science, the physical sciences. That's where it began. So clearly this slope is interpreting our data as a speed. And we're going to come back to that through physics. Speed, a velocity, v. How interesting that we did not have the speed at any point, and now because we're using a mathematical formula, we happen to know the speed. That's very intriguing. So was the speed constant? Well, we could always try different slopes. See, okay. So slope. So we can try another slope. We could take this point to this point. Okay, you get my point. It would be plus 2.4. But let's try it because example. So let's try from point 1 to point 2 to point 4. 1, 2, from point 2 to point 3. So so we're gonna write our formula. Slope equals rise over run. Point 2 is rising 2.4. Oh my god. Technology is coming along. 2.4 over during that point to that point, rose 2.4 and 2 seconds. But there was an increase of 2.4 in rise and an increase in 2 seconds in the run. Naturally, it will give us the same answer. It's the same calculation. Let's try something a little different. We're going to take the first point and the last point, or like the third point. Slope. And I'm going to write slope 1 to 3, or 1 to 4. Because it's 1, 2, 3, 4 points. So from point 1 to point 4. And this was basically slope 2 to 3. This was slope 1 to 2. So you can write like that so that you know what you were doing. Slope 1 to 4 is rise over run. Okay, so from 1 to 4. From 1 to 4. We rose how much? 2.4 plus 2.4 is 4.8 plus 2.4, 7.2. Divided by 1. From here to here is 6. 6 seconds. You divide that, you will get 1 meter per second again. Same thing, same slope. So you can basically say that because you have a constant line, you can calculate the slope a few times, but it's always the same answer. Okay, so the first example will look a lot like this. The second example, you'll have to draw your own graph again, answer some question, and then actually calculate the slope for that one. So I hope this this lesson helped in understanding the. It's a long video, I know. Understanding all of this simple mathematics. Here, the last point. The rise from the first to the last point was 14.4. The run from the first to the last point was 12 plus 12 and plus 14.4. Throw that in the formula, you get the same answer. And that will be the basic for understanding graphs for now. Thank you. Oh, and if you have any questions, you have to call me or something like that. Get my attention. Always more messages in the channel, general chat. Okay.